Remember my previous weekend projects where we made a very simple temperature sensor, and we also made an IF alignment tool. Now we're going to use part of those weekend projects to create a new project, and we're going to house it in a light bulb housing, something pretty much like this. I bought this on the internet cheaply, and we're going to use this to put inside our new weekend project, and the weekend project will be a AC powered AM radio transmitter. Yep, we're going to make our own little AM radio transmitter station, and we're going to house it in a light bulb housing like this, yeah, so that we can quite simply screw it in a lamp holder or a lamp socket, and then have it transmit music over the AM band. Now, the next question you will probably ask is, okay, well, where will the music come from? Well, that part I don't have yet, but I have something that will temporarily substitute for what I'm waiting for. So, in fact, we are going to use one of these, a tiny little portable FM radio. So we're going to use the output of a little FM radio like this to retransmit music that it receives through our AM transmitter that we're going to build. And our AM transmitter will be built around the, by now for all of you familiar, Colpitt's oscillator. So, let's get to work. I put together a Colpitt's oscillator, which you see down there, and I made it oscillate at 645 kilohertz, which is a good frequency, not too low, not too high, somewhere on the AM band where it doesn't bother too many other stations, at least not where I live. And I also put the how should I say, the current meter on to the power supply circuit to show you how many milliamps it consumes. And apparently it's very frugal. It consumes only about 2.2 milliamps at a little bit more than 9 volts. Okay, 9.2 volts. And I calculated that it outputs, well, it outputs peak to peak 10.8 volts. Yeah, you hear me correctly, 10.8 volts. So if I calculate roughly about 2 milliamps times 10.8 gives me almost 24, or I should say 25 milliwatts output power. Now, okay, I agree. Since this is high frequency, I guess I would have to correct for that too. But let's say as a rough estimate, it's okay. So let's say this transmitter is in transmitting in the order of 25 milliwatts of power, which is just fine because, well, we don't want to get in trouble with the FCC over in the States or down here with telecom and telegraph company or organization. So 25 milliwatt is just fine. I think once you start to transmit over 50 milliwatts, then you get on dangerous terrain. Okay, so well, all right, I made a tiny little power supply, which you see over there. And as you can see, it consists partly of a rectifier circuit, which you see over there. Yeah, this is the rectifier circuit. It doesn't do much more than give me a rectified voltage directly off the AC, and the rectified voltage is led into what is basically a voltage limiting circuit, which is this, and a filter circuit. So I built a tiny little filter which I hope will filter most of the 50 Hertz buzz that might come through the rectifying circuit. And you can see in the middle of the filter circuit, you can see two Zener diodes. And one Zener diode is a 6.1 volt diode, and the other is a 3.3 volt Zener diode. Together they strung in series, they give either a 9 volt regulated voltage or a 6.1 regulated voltage or a 3.3 volt regulated voltage. So I have the choice out of 3 output voltages. Now basically I will need a 9 volt and a 3.3 volt. The 9 volt powering my oscillator, which you see here, and the 3.3 volt which will power a small FM receiver like that one over there. So let's see what it does when I power it up. So I'm giving the full 220 volts from my Variac. As you can see, I'm at full voltage, and I'm pumping the AC 220, or I should say almost 240 volts AC, through a simple AC wire, which you see, this transparent wire, and through a switch, as sort of a safety switch, you could say. The AC power goes into the rectifying circuit, and the output of the rectifying circuit goes into my voltage limiting and power filtering circuit, which you see here. Okay, so I hooked up my multimeter to the 3.3 volt output of my filter. So let's see what happens when I switch on the AC voltage. So here we go. Watch the meter. There you go. So I'm getting 3 volts out of it. Now the meter, my multimeter, is obviously a little bit vacillating between 2 and 3 volts, because at the highest meter position, which is 1000 volts DC, it's not extremely accurate. Anyway, let's now test the other output, which is supposed to give me 9 volts. Here we go. The voltage you see now is the voltage which is left in the capacitors of the filter circuit. Okay, so slowly but surely the voltage will drop, but I'm impatient and so are you, so let's see what happens now when I switch it on. There you go. 9 volts. Okay, again it oscillates between 8 and 9, but again this is due to the inaccuracy of my voltmeter in the 1000 volt range setting. So yeah, I have a 3.3 and a 9 volt power supply. So now the next step will be to hook it up to my oscillator. Okay, I improvised a small oscillator which oscillates, if I'm not mistaken, at about 485 Hertz. Really, this oscillator, which is by the way an astable multi-vibrator, is really nothing else but a sound generator. Okay, I just wanted to have a constant tone that I could inject into my little transmitter, which you see here, and then transmit the signal via an improvised antenna, which is, as you can see, a very long copper wire. And that's it. So yeah, well, let's show you what it does. So I have here my little AM radio. Well, it's a multi-band radio, but which I use just to test all sorts of stuff. So let's switch it on. Okay, as you can hear, well, there's not really very much at the frequency it is tuned at. But now let's switch on my little transmitter. Okay, hang on. There you go. Well, that is the tone from my transmitter. And as you can hear, when I switch it off, when I switch off the transmitter, you don't hear anything. When I turn it on, you hear something, and that is the 484 Hertz signal, which I modulate the AM signal with. Now, I tested the distance at which I could still receive the transmitter, and it turns out that I can still receive it reasonably well at a distance of, say, 6 or 7 meters, which is, well, pretty much the length of an average living room, I would guess. Beyond that, the signal rapidly starts to weaken. So, well, what do you expect? In the end, the output strength of the transmitter, as it is built right now, is about 25 milliwatts. Now, 25 milliwatts, if you're lucky and if you have the right antenna, will take you, well, about 10 meters to transmit the signal. So a distance of 10 meters is okay. You know, I never really wanted to build a huge transmitter. Well, maybe, who knows, someday. Anyway, this is all about learning how to make a simple transmitter. Now, I'm going to, right now my transmitter is connected to my variable power supply, which you see over there. Now, you might wonder why I wrapped aluminum foil around my variable power supply. Well, that's simply because I wanted to avoid any kind of stray signal influencing my transmitter, because I've noticed that it is quite a touchy little thing. Yeah, well, certainly on a breadboard, it's very, very touchy. So I wanted to cut out any possible external influence. I connected up my little transmitter to the AC power supply, and I switched on the radio, and as you can hear, there's absolutely nothing. If you hear some sounds on the background, that's the TV, but it's not the radio. So now let's switch on the transmitter and see what happens. And that's it. In fact, the signal is so strong, it's overpowering the radio. So let's switch it back off. And there you go. Now, the fact that you hear that lowing sound, you know, the sound going whoa, is just the capacitors of the filter discharging themselves through the oscillator. But, in fact, the signal is really, really strong. Now, there is a peculiar oscillation I hear, sound oscillation, at the back of the bass tone of 485 Hertz. And you can hear it in the background. But when it's fully tuned, that oscillation is almost gone. You see? Now, whether that second oscillation of sound which you hear in the background is due to some external source of sound, I don't know. Or perhaps it's just my astable multi-vibrator, you know, that second oscillator that is simply not working 100% on the breadboard. I don't know. Now, the thing is that our proof of concept works. In other words, I can go ahead now and build a little transmitter on a small PCB and try to incorporate it together with the filter and the power supply into that little light bulb housing. And I ordered a small FM chip receiver, which I will use as a sound source for my little AM transmitter. But for now, that's it. So One more remark about my transmitter. As you all saw on my oscilloscope, the base frequency it is transmitting at, well, technically, is 675 kilohertz or thereabouts. It used to be 645, but when I changed some resistors and I added my astable multivibrator, which you see here, the frequency went up a little bit by about 30 kilohertz. I think that has to do with the fact that I changed by adding the astable multivibrator or oscillator and hooking it up to the base of my high frequency transistor. I changed its bias a little bit, whereby the frequency went up. Now, strangely enough, when I make it transmits at around 1300 kilohertz, which is really strange. So when it's transmitting, it transmits at almost double the frequency. So that is kind of peculiar. I don't know for the moment why that would be, but my guess is that maybe I'm receiving a harmonics on my radio and not the base frequency. But I still know too little of high frequency stuff to be able to give you any sensible explanation why the actual receiving frequency is almost double from what my transmitter is actually transmitting. So yeah, that's something we need to find out. I'm gearing up to cut a PCB to mount my little transmitter and a power filter. And since I got the little print board, which you see, the round one, with the light bulb housing you see over there, I have the perfect template to cut the PCB. So let's go ahead. Well, as you can see for yourselves, I more or less finished assembling all the electronic parts that I want to fit inside this light bulb casing. Now, in case you might be wondering why I used, for example, the power supply that was supplied with this light bulb housing, well, the answer is simple. Yes, I could have designed a power supply myself, but aside from maybe the odd resistor value or capacitor value, it would have been nearly the same as the power supply, which was supplied together with the light bulb casing. And also, the power supply, as you can tell for yourselves, was specifically designed to fit inside this casing. Had I designed my own power supply, I would probably have succeeded in making one which would fit inside, but I had this one ready-made, so why would I not use it? And anyway, the values used on the power supply are nearly identical to the ones that I would use with my own power supply. Anyway, as you can tell for yourselves, I cut the PCB for the transmitter part myself, and I cut it out of a piece of PCB board I bought ready And as you can tell from the top of it, it was originally a board of size 5 centimeters times 7. I had the perfect template, of course, because the original board, which was supplied with this light bulb armature, and which was intended to be used with a lot of LEDs tacked onto it, I had the perfect template for the size of the PCB. And as you can tell for yourselves, it works out quite nicely. Now, there might be a couple of parts that you don't really well, that might not seem logical to you to be on the PCB, but I'll explain it. Underneath the electrolytic, you see two Zener diodes. Now the Zener diodes are a 3.3 and a 6.2 volts 1 amp Zener diode. Now the reason why I put them in series is because if you put two Zener diodes or diodes in series, they limit the voltage to the sum of their voltage breakdown voltages. So 3.3 plus 6.2 is 9.5 volts, which is pretty much the voltage that I was looking for. Now, you see on the other side of the electrolytic, you see that blue little resistor down here in the middle. That is just a voltage drop resistor, which I built in because I want to power this LED with the voltage supplied by my power supply. Why? Well, as an indicator that it is on and that DC voltage is running pretty much the way I want it to run. Now the last part is this extra coil you see here. Now this impedance, or I should say this inductance, is here to work as a filter together with this filter cap. Its cutoff frequency, if you would calculate it, is, if I'm not mistaken, around 715 kilohertz, which is a little bit above what I hoped it to be, but I think it will do pretty much what I intended it to do. So, in other words, the intention is that it would cut any high frequency from crawling back up the power supply line and thus into the AC power line, which we don't want, of course. We don't want any high frequency to propagate up the AC line and therefore possibly interfere with other equipment in the house. So yeah, I think it will pretty much work the way I intended it to work. So it's nothing but a very simple filter mechanism. Okay, so what am I left with to do? Well, I will connect up the power supply. First, I will test out the board, okay, with my variable power supply, just to see whether it works correctly, and then I'll mount the LED. When that is done, and I tested out the high frequency part, then I'm going to wire it all up to the power supply inside the light bulb armature, and Well, that will be it for now, because like I told you a few minutes ago, the thing that I want to do is I want to build in a tiny FM receiver, which is much smaller than this. Actually, it's a tiny little PCB which is used to build an FM radio of a tiny little size, and I want to build in that radio inside this light bulb armature. Okay, I hooked up my little transmitter to my temporary low tone oscillator to modulate its signal, and I switched on my little portative radio over there to check whether it transmits or not. So let's have a go. I'll switch on my power supply, which you see over here. And there you go. It works. Now, strangely enough, now that I built in all the parts on the print board, it changed the frequency. In fact, the frequency rose still a little bit. It's now around 1600 kilohertz instead of the 1400 that it gave off on the PCB, which of course, let me switch it off first, which of course proves that when you're involved with high frequency stuff, you should always keep the connecting parts close, the connected parts close together, and keep the connections as short as possible. And it also shows that the leads coming off the electronic parts certainly influence the working of the whole high frequency part. Notably because connector leads on electronic parts are, you could say, a kind of an inductance, and they also function a little bit like little antennas. So they pick up stray signals, but they also send stray signals. Now anyway, now that it's completely built and checked, I'm going to build it inside the lamp socket, which you see here. So let's get cracking. Well, this is a sneak preview of what my next weekend project will look like, more or less, when it is completely finished. Yeah. My little AM light bulb transmitter, and well, as you can see, the LED works. I haven't hooked up my little sound generator here to my transmitter, so you wouldn't hear a thing if I now switched on the radio, because it would simply be transmitting a clear carrier signal, or if you want, an unmodulated carrier signal, so it wouldn't do a thing. You would just hear silence. But anyway, that's how it will look like once it's finished. The only element that I need to build in is the sound source to modulate the AM signal. And as soon as I have that, I'll put up another update on this weekend project. So, this concludes. Okay, I built an AC power supply, or I should say directly AC powered power supply for my little AM transmitter, and the basic schematic for it is this. Now, the only difference between what I actually built and which is inside my AM light bulb casing, and which is shown here on the schematic, is that I'm not using one Zener diode of 5.1 volts. I'm going to show you immediately what I did use instead of this. Now, two remarks, or rather three, about this power supply. I shouldn't have to remind you that it's using direct AC current, okay, or AC voltage. So it's really deadly. So be aware of that if you're making one yourself. Another is that this power supply uses one capacitor, in this case a 100 nanofarad safety cap, and I am stressing the word safety capacitor, okay? So don't be tempted to use a normal capacitor, use a safety capacitor. And if I'm not mistaken, safety capacitors are marked with an X2 symbol or a Y symbol. One of those types is meant to be used crosswise, so put over the phase and the neutral, while the other type is fit to be used in series like this. Look it up. I don't know by heart which is which, but I'm sure you'll find it. And then the last remark is, although I don't use a fuse myself in the power supply, feel free, of course, to build a fuse in if you feel like it. But if you do, then use a fuse of maximum 50 milliamps or something like that, because the design of my AM transmitter will never use more than 50 milliamps. Okay, so instead of using this Zener diode, we're going to use this part here. So instead of this, think this instead, okay? So I'm using two Zener diodes strung in series, one of 3.3 volts, the other 6.2 volts. And if you string them together like this, you can basically add up the voltages which they limit, okay? So if you put a 6.2 in series with a 3.3, you get a 9.5 volts at the output, which is perfect. The 3.3 volt I use to power an LED, and in a next update I'll also power a small FM receiver with it. The total voltage, so the 9.5 volts, I use to power my little transmitter. This coil and this capacitor act like a filter. Yeah, it blocks high frequency signals from crawling back up the power supply, and therefore polluting the AC which powers the power supply. Okay, now that's the power supply part. Now the transmitter part. Well, like I said before, the transmitter is built around a Colpitts oscillator, okay? And it's built around one active component, which is a transistor, you see here. and then it has a few capacitors and a few coils, and all the parts are listed here. Now remember, I built my Colpitts oscillator to oscillate around 645 kilohertz, and but if you want to design a little transmitter transmitting at a different frequency, well, then you will either have to use another coil, okay, with a value anywhere between 220 and 330 microhenries, or you might have to vary this capacitor here. Yeah, so capacitor 2 on my schematic. So if you vary its value between, say, 50 and 150 picofarad, you can also vary the frequency at which this little transmitter will transmit. You can forget about these red drawn parts, so I don't use them. And if you want to input a low frequency signal to modulate the high frequency, then you input it here at this point, so right at the base of this NPN transistor. Well, that's it. One more thing. If you want to go about it a little bit more scientifically, you can always use this formula here to calculate the values of the capacitors and the coil to use for your Colpitts oscillator. So that's it. I hope you enjoyed the video, and I'll welcome you back for other updates.